Today we will look at variational autoencoders and how do we train those and why at all do we need them. So let's start with a brief recap of what autoencoder is. Basically, the simplest autoencoder would be like one projection layer into which produces some hidden representation, and another projection layer which does a reconstruction of the input. And yeah, you can, these two diagrams are equivalent. And well, both encoder and decoder might be anything different from a simple projection layer. You can have some more complex, deeper net for both encoder and decoder. Yeah, so now what if we, instead of doing like deterministic, instead of producing this hidden variable in deterministic way, we can train our encoder to output distribution, like parameterization for distribution, and then we can sample from this distribution to obtain like a stochastic hidden variable, right? So our encoder in this case will output means and variances. Those are both vectors of a dimension of z we want to input to the decoder, and this means and variances would be used to reparameterize a distribution from which we're gonna sample z. And yeah, so in this case, the encoder would output, like the output of the encoder would be of twice the dimension of the hidden variable. Yeah. So here, you can see what's going on here. So the encoder outputs this h, which can be viewed as like concatenated means and variances, and then we use those means and variances to sample z. Then we input z to the decoder, and it outputs a reconstruction of original dimensionality of the input. Yeah, and what is the motivation behind using this? So in the deterministic case, like for a regular autoencoder, we let's say we have this data manifold here, and we have some input x, and for a regular autoencoder, it will be projected into some z in a deterministic way. So it outputs a single value for z, right? And this single value is like deterministically reconstructed into some x hat. So for each input x, we have only a single output, a single possible output x hat, right? And in this case, we don't have much information of what's going on between these data points, right? So we know how to reconstruct each given data point, but when trained in this way, we don't have any like don't have any control over what's going on in between the data points. So now let's imagine that instead of reconstructing this X deterministically, we first map X into Z, and then we add some noise to it. So here, this like orange bar, it represents some space in which the like Z that we will use for reconstruction may end up. And so, for example, for each X, we can have now multiple values for Z. And we still train it to be reconstructed into the original Z, right? And in this way, we enforce a structure into our latent space, right? So when the latent space is trained in this way, we have a meaningful, so we have it like a meaningful distribution over possible values of Z. And one problem here is that it's not possible to backpropagate through sampling. And this is solved by this what is called reparametrization trick. And the reparametrization trick is basically done this way. We sample some variable E from a standard normal distribution. Here it's a multivariate normal distribution of like dimension D. Then we rescale it by the variances and add means to it. So now we have some shifted Gaussian distribution, right, with mean E and variable variance Z, which are outputs of the encoder, and we can easily, like straightforwardly, backpropagate through this computation, because backpropagation is done through simple like addition and multiplication, right? And so another thing here to be considered, that we want well, the reconstruction loss here is computed between X and X hat. And to make reconstruction simple, we could like separate this like kind of stretch this axis Z1 in such a way that for each Z, for each X, we have like well separated region of these into which we can map it. And this is not useful for us because it's like ruins what we were trying to achieve. We were trying to enforce some structure into latent space, and by minimizing reconstruction loss, we basically are removing this structure. And to avoid this, we add another term to the loss, which is this relative entropy, or Kullback-Leibniz divergence of distribution of Z as compared to standard normal. And in this way, this Kullback-Leibniz term will push these E and mean and variance towards standard normal distribution. And reconstruction loss will pull it pull those these apart to make them useful for the reconstruction.
Arto,
so,
could you go? Arto, yeah. Could you go back one slide, please?
Sure.
Yeah. So the reparametrization trick. I mean, it seems nice, but I mean, how do you know the expectation of Z and the mean of Z? I really don't see how it works in practice.
Right. So we should go one slide back. The expectation and variances are basically predicted by the encoder. So the E and V of Z are outputs of the encoder, and those are specific to our X. And the encoder is trained to output means and variances which correspond to given X, right?
Okay, yeah.
So, yeah. Now to this Kullback-Leibniz divergence term. So we have a reconstruction error loss, and let's consider this term in more details. Basically what he was telling that this reconstruction term is pulling those bulbs, which each of these bulbs correspond to some Z distribution, and reconstruction loss pulls those Z's apart, because when they are well separated, it's easy to get good reconstructions, right? And now let's see what this part does. So there are two terms of it, and one is this variance of Z minus logarithm of variance of Z minus 1. And basically here is the function which corresponds to this V. Here we denote it as V. And this function has a minimum at 1. And it grows less steeply towards higher values, and it grows really steep with strongly for lower values. So and how this can be interpreted, that it's hard for us to squeeze this bubble, right? So also it when this bubble grows, we move here, and the loss becomes larger. And when we squeeze this bubble, we move here, and again the loss becomes larger, right? And basically, when this term is close to 0, we will be outputting a point for this for the parameterization of Z, and the loss term would be very, very high. And this term here, this is just standard parabola with a minimum at 0. So maybe it's, oh yeah, here it is in the next slide. So this U part here, it's just a parabola with minimum at 0, and it just makes it that our distribution is pushed to each of these bulbs are pushed towards the center, towards the 0 mean. And here it's shown here that this relative entropy term just packs all these bulbs. It packs it inside some kind of area, region of space. And in this way, we should get tightly filled space for the hidden variable Z. All right, and
Arto?
Yep.
What is the intuition behind enforcing a structure like this?
Yeah, we will see it maybe when we go to the practical notebooks. So there would be a nice demonstration of it. All right. So let's check if we went through all the information here, like theoretical part of it. Yeah. So now let me just quickly open the relevant notebook, and I will reshare my screen, and we will go to the practice. And yeah, I found it most useful for both understanding what's going on, why do we want to do this, and also how does it work. So yeah, I will just change the, okay. Oh, I will just change the screen I'm sharing, and let me fix it. Here we go. Right, you can see it, right? So one moment here. Okay, I'm trying to fix my virtual background, but it doesn't work, so probably, yeah. All right, let's go back to the, yeah, I guess I will just remove the video. Let's go back to the notebook. All right, so here we do some imports and define some functions to display the images and load the data. This is MNIST data set. And here, let's check the model definition. And so what we have here is simple decoder, which is just a multi-layer perceptron with ReLU nonlinearity. And the decoder is just like mirroring of the encoder with a sigmoid in the end, because we normalize our images to be between 0 and 1, right? And the sigmoid ensures that our model outputs values between 0 and 1. And here you can see this reparameterization part. And the reparameterization part is, so we train our model to output the logarithms of the variance and the means. And why logarithms of variance? Because our encoder outputs like all the possible values, but the variance can be only positive, right? And by taking the log of it, we can just simply output any real number and convert it into the variance by taking an exponential. So hopefully that makes sense. Yeah, and as you can see, the reparameterization is done. So this part is done only during training, and at validation. So at the validation time, we simply input the means predicted by the encoder. We ignore the variance, and yeah. So probably this makes intuitive sense, because when validating the model, we want to get the best reconstruction we can, right? So here is the forward pass is simple. So our encoder, it outputs means and log variances, and then we reshape it to make it easier for us to get this. So we get separate means and log variances and feed them to this reparameterize function and obtain z. So now z is not deterministic, but stochastic, right? Because we do here we generate this epsilon, which is from standard normal distribution, and then multiply it by standard deviation and add mean. Okay, and then it is fed into the decoder. So here we define some optimizer, learner rate. All right, and the loss function here is a reconstruction term, and this KL divergence term. And I just did a quick derivation of this. If you were wondering how did we jumped from this part, which is KL divergence between of P from Q, or how it's pronounced. Yeah, so KL divergence between these two distributions, and it may be so. This is by definition it's expectation over P of x of log P of x over log Q of x, and I don't know if you are interested in these parts, you can like check it yourself, or I can explain these steps. Yeah, but so basically with some simple steps here, we can get to this 1/2 minus multiplied by negative logarithm of this variance minus 1 plus variance plus mean squared, and here it is. All this thing. Yeah, and my notation here is not really the best you could imagine. Sorry for that, but yeah. So instead of this sigma, we should have this covariance matrix. But in our case, it is diagonal, and it might be easily like imagined that this is a diagonal matrix. With containing all the variance components for multivariate Gaussian. All right. So, and here we have this training procedure, and I trained it for 50 epochs. So I guess we're not gonna just rerun it, at least for now. Maybe after we view the results first. Yeah. So yeah, we can. See this training, how it goes, and here are the outputs. The first, these are inputs, the first row, and the second row are reconstructions. And I just collect these images every 10 epochs. We so we can see how the reconstruction changes during training. So this is epoch 10. Epoch 10, you see the reconstruction already quite good, but somewhat blurry. And then as we progress, here you can see that most of the reconstructions are really pretty good, but this one is not so good because probably this 2 is not very nice representative of any number, really. And as we progress, you can see the reconstructions pretty much remain, yeah, all right. Here. So these are some examples from the final output of the model, and you see we had some kind of noise here, and the model removed it. That's like probably a good sign. And yeah, reconstructions are pretty nice. And now we can just so here we simply generate some random variables of dimensionality of our hidden variable z, and we feed it into the decoder and plot the reconstructions. So here you can see that they are not so good, but these are just random variables from like our standard normal distribution, and some of those like are quite similar to some numbers, right? So here a bunch of zeros, and this looks kind of like 9, and this looks like something in between 7 and 1. Here is kind of 8, 3, 4, or 7 again, and again. Yeah. So these are reconstructions from feeding just random noise, random standard normal noise into the model, into the decoder. And here we take a couple of numbers. Here we just display a batch, select 2 numbers. I choose this 9 and 5. Here, so this would be our initial number and its reconstruction, and our like final number and its reconstruction. And here we basically move in the hidden space. We move over these. This is just a linear interpolation between z for 9 here and z for 5 here. And you can see as we move through hidden space, here we have this 9s, 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 and still 9s. And as we move towards 5, probably somewhere at this point, we start getting numbers which are closer to 5, right? So, and so this is the answer. Why do we want this packed hidden? So why do we want to enforce the structure on the hidden space, right? Because this helps us to now our decoder is a generative model, and we can feed some z to it, and so we can sample from it, right? We can sample from this generative model, and this wouldn't be possible with standard encoder, autoencoder, because for regular autoencoder it has like meaningful reconstructions only for like some concrete inputs. But here we have meaningful reconstruction for all the space between the inputs. Yeah, so somewhere just in the middles, as we see here, it might be not so meaningful, but it has some structure, right? And this was a really simple model. And when working with images, we probably could have tried convolutional model, and yeah, that's what I did. So I will just open another notebook here, and yeah, while it's opening, we will move further and inspect the other interesting thing here. So here we use this algorithm called TSNE to visualize our hidden space, right? Z space. So we pick a bunch of, like here we pick 1,000 of axes from our data. And we take those means, like the means of the from the outputs of the encoder for those axes. And then we apply this TSNE algorithm, which it is designed to, it's kind of similar to PCA, but it's specifically designed for visualization of the data. And here we compress our 30-dimensional hidden space, or 20-dimensional, I think it was 20, right? Let me check it. Check it here. Yeah, we had 20-dimensional Z, and we just compress it into 2 dimensions. And here are some visualizations of the structure of the hidden space at epoch 0, 10, and 50. And as you can see here, at epoch 0, the data is distributed quite uniformly, but it's not really well structured. So here you see that the numbers are badly mixed. And so this is untrained model, right? Just random weights. And you see that even with random weights, we have some clustering, but yeah, it's not really so good. We cannot be sure which point correspond to which number exactly. Those numbers are badly mixed, right? And here you see that at epoch 10, we have some better separation of the hidden space. So each cluster corresponds to some number here. And yeah, and let's check what we have at the end of our training. And you can see here, for example, that 9s and 4s are, here you see 2 clusters for 9s, and here is this cluster for 4s. And yeah, it probably makes sense, because sometimes you like, as you draw 4 or 9, they might be very similar, but still there is this clear separation between 4 and 9. And kind of the same for 8. Here you see this 9s are close to some 7s, and here you see that 8s, 5s, and we kind of can travel through from 8s to 3s and through 5s, right? This is kind of remember that this is 2-dimensional visualization of our high-dimensional hidden space. So in reality, this is 30-dimensional hidden space, and it's not this simple, but this visualization can give you like good intuition of how this compression, enforcing structure on our hidden space works, right? And here I just displayed some smaller images because they look nicer, you know. These bigger images are just too pixelated, and when you plot smaller images, you can get better results, like more visually appealing results. Probably it's just the same data, but it looks nicer to my eye. And here you can see that, again, these are random samples from we just randomly sampling from our decoder. And yes, some numbers are pretty reasonable numbers, look pretty nice, right? And here another bunch of examples of reconstructions. And so for concrete like numbers, the reconstructions are good, but also let's check this convolutional autoencoder. So the idea is the same. We only change the encoder and decoder here. And here I just construct the simplest possible convolutional encoder. I just try two convolutions, like mostly with kernel of size 3. I only do the first convolutions with kernel of size 5. And in the end, I get this 2 by 2 by 5, 2 by 2 by 10. So this D here is 5, and we have this doubled here because we want means and variances for sampling from it. And yeah, so the output of the encoder would have the same effective dimension here as for the multi-layer perceptron we had before. And yeah, but this time it's produced by convolution, and the decoder is just like kind of mirrored stack of inverse convolutions. If you, yeah, maybe those who read that Aurélien Guéron's book, remember we had discussion of this usage of transposed convolutions, and here I just use them. You can like when upsampling image or like not upsampling but moving from lower resolution to higher resolution here, right? From lower size to higher size here, there are a bunch of techniques you can use, and probably this inverse convolutions are not the best one, but like it's one simple way to do it.
Sorry, in the original model, yeah, like it had like D equals 10, and then you doubled that because 10 were for the means and 10 were for the variance.
No, we had D equals 20 here. Let me just scroll to it. Yeah, here we had D equal 20.
Yeah, sorry, but like 10 of those are 10 for the mean and 10 for the variance, aren't they? Because of the fact that you've got like 10 digits.
No, we have here. It's also multiplied by 2.
All right, so you don't need
the dimension of means would be 20. So the D is dimension of hidden space, and we have it doubled for sampling, like to for our decoder to output means and variances, right?
All right, you don't need to have in the hidden space sort of one category per digit then, no?
Do we need to have one category per digit? No, we don't. This is basically like a vector representation of our input. So this is kind of compressed version of our input, right? And it's a vector of dimension 20 in this case. And by like increasing this dimension, we make it simpler for our model to kind of reconstruct. And by decreasing it, we like make it like enforce stronger constraint over the model. How should it compress the input, right?
All right. Okay.
So if you think about this like undercomplete autoencoder, if we remove this sampling part from it, we would have pretty much the same kind of process, but without sampling, we would. So you can think of undercomplete autoencoder as output in only means, right? But here we output means and variances. But the dimension of the hidden this latent variable is the same. So again, we have this undercomplete autoencoder.
But to Steve's question, I guess the point is there is no relationship between the latent variable dimension and the number of classes necessarily that you're trying to predict. That is, just because you have 10 digits doesn't mean that's the reason you're choosing DS20. The DS20 or the latent variable dimension.
So this is why I'm bringing up this relation to this undercomplete autoencoder. So when we do this undercomplete autoencoder, it's like kind of a non-linear version of PCA, right? So the choice of the dimensionality D here, it would depend on their like what dimensionality is needed to represent our data. And so their like initial input dimension of like in pixel space, we have this input dimension 784, right? But if you apply PCA to the MNIST data set, you will observe that the first, I don't know how many, but some maybe 50 principal components correspond to very significant part of the variance of the data, right? So the effective, ideally we would set D to be the effective dimension of our underlying data generating distribution, right? Data generating process. But we don't know it exactly, right? So we should choose this D in accordance to the structure of our data set.
But the challenge is in the general case, we don't know that, right? He discusses, for example, in the while predicting human faces, if you know for 50 to 60 the underlying dimensions because of the musculature related to faces, therefore you choose the dimension of the latent space to be somewhere in the 50 to 60. But extending Steve's questions, I guess the real question is in the general case when you don't know the distribution, is this just a trial and error or there's still rules of thumb for choosing the dimension of the latent space?
Yeah, I guess you can probably gain some intuition by doing this, as I said, simpler dimensionality reduction, applying simple dimensionality reduction methods. And so it would probably like kind of describe what D should you choose, right? So you can try some, as I said, you can try PCA and you can try other like maybe some non-linear approaches to that, and you can choose some value for D which would be like compatible with what you observe. So we want to be able to represent like this variance of your data set, right, by this vector of dimension D. And so I think that understanding the number of independent components of the data generated process should be useful for choosing this D. But that's just my intuition about it. I cannot like really say what's going on practice. Yeah, I guess like most of the deep learning now, it's usually more of like an empiricism and art rather than exact like saying like math, right? All right, so yeah, back to this convolutional variant of our model here. Okay, so yeah, that was the second run I done with this model, and yeah, so here I played a bit with this beta, and what is this beta parameter? Let's get back to our loss function. We have two components of our loss function, and one corresponds to this reconstruction error, and he chose to use binary cross entropy, and this is our this KL divergence term. And we can balance this by some hyperparameter, right? And by default, it's 0.5, just if we don't have any weight to it. But we can change it. And in this way, we will affect basically how tight we want to be, our distribution to be. And like playing around with this can give you some intuition. So here I set the beta to high value of 3, like I set it higher compared to what we had before. And what it means is that we like put more effort into keeping this tight Z space, right? Of tightening the Z space. And here you can see that the reconstructions, so again, these are random samples. And first thing you can observe, probably these look better as compared to the variant we had before. And the second one, they are kind of blurry here. And that is because we had this stronger KL divergence term in component of in our loss. Yeah, and here again, I just move from in this hidden space from 8 to 9. And you can see that it's basically, it do not change much here. And here it just switches to like, here it's still kind of 8. Yeah, so it's 8, 8, 8. Here it's somewhere in between, and here it's 9. So that's pretty nice, right? And here again, here is this visualization of our Z space, and you can see that it becomes tighter. So notice here that we have different numbers on the axis here and here. So this one is tighter, a bit tighter, and also it like you can see that it is probably better filled here, and you can see another thing is that ones here are just like far apart from everything else. So probably that this means that really, yeah, it makes intuitive sense as ones are very distinct from other numbers. And yeah, and the closest to ones are some 7s here. So that's probably makes sense. And here is another run for lower value of beta. And let's check. And as you can see here, the reconstructions are worse. And this is probably due to the fact that we had like lower rate to our KL divergence term, and the hidden space is less tightly packed. And yeah, so most of the time we just hit some not very meaningful region of space in their hidden space. Yeah, and notice here, so these are the reconstructions and step 0, and you can see here this pattern. It's due to this upsampling, like transposed convolutions we're doing, and like by default, it results in this. I don't know how it's called, checkboard effect or something like that. Yeah, but then we start getting, yeah, but here you can see that reconstructions are less blurry in this case. Yeah. And again, let's check another variant of this hidden space visualization. And with lower value of beta, it is less tightly packed. And this connects with the like lower quality of random sampling from our decoder. So using it as a generative model, right? And yeah, so and yeah, so that's basically it for variational autoencoders. And do you have any questions? Yeah, and I have a small, another like small thing here. So I took a look at VQWire. This is like another variant of autoencoders. It's called vector quantized autoencoders. And yeah, so we can take a quick look of at what that is. And meanwhile, we can just have another run of this training to see the results as it progresses. Yeah, and I just changed this loss function here a bit to return separate components for the reconstruction term and KL divergence term, just to so that we during training we can see what is the ratio here. And how does it change as we vary beta? So that's one that is one interesting thing to play around with. Also, okay. So let's move to this variational autoencoder thing, and in variational autoencoder, vector quantized. Variational autoencoder, we have a bit different approach to constructing this thing. So here the idea is instead of making the instead of sampling from the distribution returned by encoder, we learn a kind of dictionary for our embedding space. And what they do here, they output a vector, and we have this bunch of so this would be vector quantization. We have a bunch of embedding vectors here, and we can represent each z by some by average of the closest vectors from our dictionary, and yeah, this is kind of another way to construct this generative model from our variational autoencoder. Yeah, and here is a say that this operation, like look up into the this embedding space, which might be like viewed as a dictionary lookup. It's not. It is not a differentiable operation. And what the authors did, they just made this gradient to travel directly from from this quantized version of z directly to the output of the encoder, and also learn as they learn this dictionary by yeah. So here is this vector quantization learning algorithm, and they use it to learn the dictionary. Okay, so hopefully that makes sense. And here is this like implementation of simple VQI. Here it's like small autograd function to make this to make the gradient go through this quantization operation, but we just don't we don't pass the gradient through all these computations, but just copy it directly from Q here to Z. Yeah, all right, and here we have this we have this embedding, which is basically a matrix of size number of embeddings by the dimensionality. Here, this dimensionality would be kind of similar thing to what we had before for D value. And we compute the distances between output of the encoder and all the embeddings, and then we choose some closest embeddings and average those to use as input to our decoder. So the input to the decoder would be like a mean of the combination of closest embeddings learned. And here's this implementation of the loss function from the paper. Yeah, and we do some training here. Again, we can check their how reconstructions improve during training, and we can try, yeah, but here it doesn't make that much sense sampling randomly from this model, because we don't learn like to reconstruct from random. So here you can see how would you see that this outputs of the decoder are kind of like numbers, but yeah, they don't make, so he inputting a random noise into the decoder here does not make sense that much. And but here you can plot the dictionary we learned, and this dictionary is we have this 40 embeddings of dimensionality 30 here, and that was just some arbitrary choice I made. Yeah, I didn't had much time to fine-tune these parameters here, but you can see that the model learns kind of bunch of numbers here as we train it. So these are learned. This is kind of our vocabulary, and in case of digits, this kind of makes probably I didn't do the best job of choosing the hyperparameters here, because probably we want to this dictionary size to be smaller compared to our kind of number of distinct parts our output can consist of. And in the paper, this was applied to CIFAR-10 dataset, and here you can see the results they obtained by train. Here are the results from ImageNet, like this inputs and reconstructions, and there should be some samples. Yes, here are some samples from this model they had. You can see that it can produce some realistically looking images, and here you can see some kind of mess of a car, right? But some images might look really like something meaningful. So
what's the main advantage of this, Arto, that they call out in the paper compared to doing it versus doing it the traditional or the previous way?
Yeah, we can here in the motivation they speak about it probably. Yeah, so they call that this there is this thing called posterior collapse, and variance issues, and probably that sends us to the variational autoencoder, and yeah, so also this this kind of model, I think it was very similar kind of model was applied to if you recall this DALI paper. Let me open it from I guess it's from OpenAI, right? And so what they did, they learned to output images from text descriptions. And how it's done? So they have something very similar in its sense to this vector quantized variational autoencoder. And yeah, let me try to find if they have some nice representation of how it works.
Yeah, so I was intuitively thinking that it might help be more precise in terms of what it's targeting in the output space because of the dictionary having discrete. Does that kind of resonate with this example, or is that intuition completely wrong, or do you know?
Could you repeat it, please?
Sure. I was saying because of the fact that in one case you have to move through the latent space in terms of distributions, whereas in this case you move through that space in a dictionary which has discrete elements. So you're able to more, for lack of a better word, more precisely control what you get or what you expect to get as the output when you're choosing specific elements in the dictionary.
Yeah. I guess exactly that's the benefit of it. And yeah, why I was bringing this paper up, because I don't see the nice nice picture here to explain it, to help me to explain it. But what they did, they learned a joint vocabulary for texts and yeah, they learned a joint vocabulary for text and images. So both images and texts are mapped into this vocabulary, and the texts are outputted by some. Yeah, I thought there was this, but yeah, whatever. The text is outputted by, for example, transformer model, like GPT or something, and the images is encoded by some convolutional model, for example, or you can use probably also image transformer. So we have two separate models for for images and for text, or we can have this joint model. It doesn't really matter, but the thing is, we learn to to match the vectors for text and vectors for images, and in this way, at the generation stage, we can input the text, get the vector representation of the text, and then input it into the decoder and get the image described by the text, right? So that's pretty cool. And this DALI showed really cool results. They have an interactive web page where you can go and play with this kind of model outputs. And yeah, here you can check out the generations for some text inputs. So this is called zero-shot text to image generation. We just take this text, a very cute giraffe making a funny face. So now we put this text into our text encoder and get the vector of it for it. Then we take this vector and put it into the decoder. And yeah, because it was learned jointly with the image encoding and text encoding were learned to be matching. Now the decoder can generate this imaginary giraffe, and yeah, that's the result. And you can imagine a bunch of other applications of similar kind when you learn this rich dictionary and get some control over your generation by learning that, by choosing the elements from the dictionary to input to the decoder. Yeah, so yeah, the model I made here, it's not really that great for demonstrating some of these properties of VQI, but yeah, maybe I will try a couple of more hyperparameters and maybe change it to be convolutional too. And yeah, if I get some funny results, I will share it later.
Yeah, maybe you can combine it with fashion MNIST and then follow the DALI paper to generate those images based on numbers you provide.
Yeah, and you could just try kind of a couple of things, maybe. Yeah, so we could like add this text input here, right? So we can like compute a simple encoding for a word and for an image, and then we could like take a word and try to generate image. Yeah, we could even try just to you know, generating numbers from text input. That would be yeah, like simplest probably use case. And yeah, that wouldn't be really that amazing, because there are really easy ways to do it. But yeah. So basically, this approach allows you to condition your generative model on some input, and you can like learn this all the parts of your model jointly. That's interesting. All right, so are there any questions about like theory behind this, or how does it work? So if not, I guess.
Thanks, Arto. Great job. And people have asked for the notebooks as well, so you can share them in the Slack if you can.
Yeah, sure. I will share it after the session.
Okay, thank you. Thanks, everyone.
Yeah, thanks, everyone.
Thank you.
Cheers, thanks.
Goodbye.